I want to continue. We are still in Chapter 2, Course Structure, and I want to remind you of some of the notation. No, that's not the right one. Huh? Okay, so time frequency shifts. Okay, time frequency shifts. The main object, this is the only notation we absolutely need. Then, okay. Then we look at sets of time frequency shifts with respect to a given lattice, Gabor system. In the applications we had rectangular lattices. The structure theory works for arbitrary lattices in time frequency space. Okay, so we are interested in Gabor frames, the sampled short time Fourier transform, the L2 norm of these inner products should be equivalent to the L2 norm of F. And we are looking at resequences, sort of the dual statement. We look at series expansions, and the 2 norm of the function should be equivalent to the 2 norm of the coefficients. So let's see. So, and yesterday I spent most of the lecture proving the duality theorem for Gabor systems. So if you have a lattice given by a basis, a matrix A, then there's an important object, the adjoint lattice, appearing in the proofs. So the adjoint lattice is basically, you take A transpose inverse, applied to Z2D, and then you basically change coordinates via the standard symplectic matrix. So this is the adjoint lattice. We saw it appear in the proof of the duality theorem, essentially when we look at how 2 time frequency shifts commute. And so this is the fundamental statement, the duality theorem for Gabor frames. So L2 function, non-zero, and lambda lattice in time frequency space. Then the following 3 statements are equivalent. The Gabor system with window G and lattice lambda is a frame. Equivalently, the Gabor system with the same window and adjoint lattice is a resequence. And the third condition is the biorthogonality condition. There exists a dual window gamma in L2 such that the corresponding Gabor system satisfies the upper frame bound. That's a technical condition to make sure that certain sums converge and certain operations are well defined. I didn't go into that. And the main condition is that gamma size, the biorthogonality condition, gamma is orthogonal to all non-trivial time frequency shifts of G with respect to the adjoint lattice, and the normalization factor is important. So what I indicate, yesterday I showed you a proof outline for the equivalence of 1 and 3. Equivalence of 2 and 3 I'll indicate today. That's a formality. But in the equivalence between frame and biorthogonality condition, we saw the main ideas appearing, and the rest is sort of technical abilities. So with that outline, all of us should be able to complete the proof rigorously. That sort of. But the ideas should be clear. Essentially, it's Poisson summation formula applied to the right function and understanding how the Fourier transform of the product of short time Fourier transforms looks like. Yeah.
Can we find an example where gamma is not Bessel, where this holds but this is not?
Well, yes, you can. For example, the Gaussian in the critical with critical density. you have a dual window, and you basically have the frame expansion, except that it doesn't hold in L2. So that's with Georg Zimmermann. Yeah. Just to show you. So here we have the frame condition. So discrete L2 norm of inner products is equivalent to continuous L2 norm. And that holds, and here is the lattice lambda. That holds if and only if we have sort of the complementary statement. Here we have sequences inside. Here we have function inside, linear combinations. And the continuous L2 norm is equivalent to the discrete L2 norm. So even in the formulations, you see a certain duality. Let's see, anything else? Okay, I think I can turn off the monitor now. And perhaps okay. So here I'll continue in a, should I say, random order of my sheets of preparation. Yeah?
Does this duality is stated for the other norms? Like if you have frame condition holding in some norm, will like the opposite statement be true in another norm?
Let's see, the norm equivalence, if you have a frame with suitable window, say in the Schwartz class, then these norm equivalences hold in different norms. There's a special class of function spaces, so-called modulation spaces, and say a distribution is in the modulation space if and only if the frame coefficients satisfy the corresponding discrete conditions. And under the same conditions, you know that the corresponding series expansion with these discrete coefficients, say LP, is equivalent to the corresponding modulation space norm. And these two conditions being equivalent, yes, they are, because if you have a frame with suitable window, then you have automatically all the normal equivalences for other function spaces. So if it holds for, say, a modulation space with parameter P, then you can go to L2, apply duality for L2, and go to the other one. So yes, the answer is yes. But that requires an extended theory of localized frames. And that, let's say here, basically I show what you can do with Poisson summation formula. When you go to function spaces, distribution spaces, and apply this, you need tools from Banach algebra and pseudo-differential operators and whatnot. So there you need different tools, and they are, well, say, a bit more advanced harmonic analysis than what I can present here. Is that assumed? Okay. So let's see. So what I want to show you is that the biorthogonality condition is equivalent to the Riesz sequence property. That's basically playing with the words. And so let's see. Okay, suppose that we have a Riesz sequence on the adjoint lattice. Then we know, well, that's equivalent to saying that the Gramian matrix, so that's the matrix with entries pi pi nu G, pi mu G, mu, and nu in the lattice is invertible. on L2 of lambda naught. So that's equivalent to saying Riesz sequence, or you can take it as a definition. So this means there exists a C in L2 lambda naught such that I can solve this system of equations. So delta, okay. So now let's write this in coordinates. This means that sum G mu nu C nu equals delta mu 0. So what is this? This is sum pi mu G pi mu G with coefficients C nu. Okay, well, let's write it outside. Equal delta mu 0. And now if you combine this and call this linear combination gamma, then you have the biorthogonality condition. So so this is sort of just translation of different languages for Riesz sequences. And if you have biorthogonality, so if gamma pi mu G, I omit the normalization factor here. So I would have to write, okay, then sorry, I can also apply time frequency shifts here. So you can bring this over. Product of two time frequency shifts is again time frequency shift, except for a phase factor. We did these calculations yesterday, so there's a phase factor of modulus 1, which doesn't matter because if mu is equal to nu, then this is 1. If mu is not equal, and I don't need the phase factor, if mu is not equal to nu, then this inner product is 0, and the phase factor doesn't matter. So this is delta mu nu. So this means these two sets, or these two Gabor systems, are biorthogonal, and if you have f equal sum a mu pi mu G, then as with orthonormal basis, you can write, let's write a nu here. Here we can write a nu as f pi mu gamma. Okay. So first of all, the biorthogonality guarantees that coefficients are uniquely determined. Simply take inner product with the biorthogonal system, and the rest is, of course, okay. Okay, and now you need the assumption that gamma is a Bessel window, so that this possesses an upper frame bound, because then if this system possesses an upper frame bound, so this is part of the assumption, then you have that a 2 norm squared is less than or equal to f 2 norm squared, and that would be the important part of the Riesz sequence property. Okay, so that completes the proof indication or proof ideas for the duality theory. So now I want to give you one more tool to check whether something is a Gabor frame or not. Yes? Here? That's part of the definition. This matrix is invertible on L2. That's equivalent to Riesz. So, if you want to understand and check whether a Gabor system generates a frame or a Riesz sequence, well, one technique that has been used is to construct some dual window. In certain cases that can be done easily. I hope that I'll have time to show you one easy example. For rectangular lattices, I would like to present or show you how a well-known characterization of Gabor frames for rectangular lattices follows from the duality theory. So, well, it's actually, nowadays it's a corollary. It used to be used to require long papers to prove this. So, we take a window in L2, alpha beta positive. The lattice is now rectangular lattice. So shifts by multiples of alpha, modulations by multiples of beta. And the following conditions are equivalent. So, the Gabor system with a rectangular lattice is a frame. That's what we want to know. And secondly, there exist positive constants A, B, such that, okay, so sum over J in ZD, sum over K in ZD, CK, G of X plus, can you still read this? So this here is equivalent to the 2 norm of the coefficients. So for all finitely supported C, for all C in L2. And the matrix here, so that would be P, what else? Such that for almost all X in, well, let's write RD. There's some periodicity, so you can restrict the X to a cube. So this here is, so now you look at the family of matrices. Ron and Shen they call this pre-Gramian, although it has nothing to do with the Gramian associated to a set of vectors in a space. So this is a pre-Gramian, and in short you basically could say that Px applied to C is equivalent to C2 for almost all X with constants independent of X. The independence of these constants of X is important. So if I say this for Akram now, this is a matrix that comes up in the sampling in shift invariant spaces. So there's a connection between checking whether a window generates a Gabor frame and a sampling problem in shift invariant spaces. So this is essentially the master tool of Guido Janssen. Whenever he proved something about frames, then he either constructed a dual frame, a dual window, or used the analysis of the pre-Gramian. There, okay. I'll prove 2, 1, and leave the converse implication up to you. Yes? Yeah. Okay, so these are exactly the technical details. So G generates a Riesz sequence. So it's not an arbitrary G. It's, if it generates a Riesz sequence, it already has to satisfy certain properties. Secondly, in the assumptions, when we don't use the canonical dual window, which is has an upper frame bound, then we have to assume that the gamma has an upper frame bound. That's an assumption that's stated explicitly in the duality theorem.
Ah, okay.
Yeah. Otherwise, it's not true.
Well, one could show it maybe with the localization arguments for this matrix G, and if you're using inverse localization with inverse matrix.
Well, then the G is already so nice that everything is true anyway. So but well, let me emphasize once more, these are not rigorous proofs. These are proofs, and it's our task as sort of mathematicians to find under which conditions these proofs work. But without knowing exactly, without having an idea how to prove things, the best conditions don't help you. So my ambition is to show you the main lines of proof and leave sort of all the pedantic question about is it well defined, under which conditions do things converge. I'll leave that to you because we all know that reasonably well, I hope. But of course, the danger is that you are going to complain that this is, I don't say everything that needs to be said. And that's true. So we go back to this criterion. So according to the duality theorem, it's a Riesz sequence. So first of all, what is lambda orthogonal? So let me recall how. So in this case, the matrix is alpha, beta, 0, 0, and these are d by d blocks. Okay. So the inverse, so this would be A. So the inverse is 1 over alpha, 0, 0, 1 over beta. Transpose, nothing changes. And then we have to multiply by these blocks here. So this just changes. Let's see. Let's see. Do I have to do that? You get 1 over beta 0, negative 1 over alpha 0, and that applied to ZD, applied to Z2D, gives you the lattice 1 over beta Z2D cross 1 over alpha Z2D. Okay? So this is applied to Z2D. So in the first coordinate I get multiples of 1 over beta. In the second coordinate I get multiples of 1 over alpha. Okay. Now we have to look at some CKL. So modulations by multiples of 1 over alpha. So modulation by multiples of 1 over alpha. So T. And then we have translations by multiples of k over beta. Okay? So this linear combination has a 2 norm that's equivalent to the 2 norm of the coefficients. Now I write it explicitly in terms of coefficients. So the L2 norm of this, I should do it in dimension 1. Okay, so, sorry. Okay, I spent too much time on the slides yesterday, and that of course takes time from thinking about this. So I assume 2, so I assume this here, and what I'm interested in is to show that this expression is equivalent to the 2 norm of the coefficients. So let's reformulate this a little bit. First of all, we notice that, well, these are L2 coefficients, so this is a Fourier series with L2 coefficients. And so I write that if I do the sum over L, I have a periodic function with period alpha. Okay? If I carry out the sum over L. So the next thing is I periodize the whole integral. I write that as integral, say, over 1 cube of length alpha, sum over j. Well, could write the sum outside or inside. And I look at translates of this cube. That amounts to a coordinate transform here. So first I have the sum over the translates of this cube, and then I make the coordinate transform. If I shift by a multiple of alpha, nothing changes here because that's periodic. So I have mu k of t, and here I shift by alpha j. Okay, j in z d, k in z d. So let's see, minus k over beta squared dt. So this is the same. Okay, now if you assume that 2 holds, this condition holds for almost all C, then this here is greater than or equal to some constant A times sum over mu k t absolute squared over k. Okay, and then I integrate over the cube. Okay, so I integrate over cube. Okay, now the 2 norm of each of these functions is the sum over L. So I have sum over k, sum over L of the absolute squares here. So that is up to, I think, a factor alpha, the 2 norm of the coefficients. You look very critical, Olga. Okay, yeah, okay. Any more doubts? So if this condition holds, and this is a condition that requires only the values of the window itself. It's somewhat transparent compared to, say, the biorthogonality condition. If this condition holds, then we have then we know that the corresponding Gabor system is a frame. I want to leave it at this. The converse is a little bit yes, here you need the uniformity. As soon as you sort of you don't have uniform constants, you can construct counterexamples. So I think these few lines show you that this is an important object in the study of Gabor frames, and in fact That's all you have to understand for rectangular frames. This condition is equivalent to frame property. I showed you one implication with a little bit of faith and perhaps of work for you. You can prove the converse. But once you have seen that the sums here are related to the pre-Gramian, I think it's plausible that you can go back. So this is a good time to air the room. So there are about, let's say, 15 or 20 criteria to check whether a Gabor system is a frame or not. And they are usually in publications, they are proved from scratch. But I claim that once you have understood the duality theorem, you can derive them as a corollary from the duality theorem. This statement here, well, was found by Janssen and Ron Shen, and well, you may want to look at the original publications. I find it much easier to take the duality theorem as sort of the fundamental theorem and derive all the other characterizations from the duality theorem. I think that's for the theory, the most important characterization. I don't say it's the most useful one. So there are tools to check, or to try to check when a Gabor system is a frame. And so the next question is, well, what can we say in general about Gabor frame? Given a window, what can we say about the set of lattices? So for that, I want to give a definition. So fix G in L2 of Rd. And then I define two sets, script F with full. So that's the set of all lattices in time frequency space such that, sorry, I should write a G here to indicate the dependence on the window. So this set consists of all lattices such that the corresponding Gabor system with window G is a frame. And omitting the subscript, this is the set of all alpha beta in 0 infinity squared. So all positive lattice parameters such that the Gabor system with rectangular lattice is a frame. Okay. So these are definitions. This is what we are interested in. Given a window, for which lattices do we obtain a frame? For which rectangular lattices do we obtain a frame? I call this the full, and the first one is the full, and the second one is the reduced frame set. So this is actually the question we want to understand. Which lattices, which rectangular lattices generate frames when the window is given? And let's see. Of course, you can do the same for Riesz sequences. Let's write R here and write Riesz sequence here. Let's write R here and Riesz here. So we could also ask the alternative question, which lattices generate Riesz sequences. It's no new question, because by orthogonality we know that we just have to take, if we know the full frame set or the frame set, then by the duality theorem we know the corresponding sets for Riesz sequences. Okay, so if for a given window G we know this set, we know everything about the Gabor analysis with this window. Okay, knowing this set amounts to a complete characterization of all lattices that generate a frame with this window. So that's, in a way, I think that's the ultimate goal in Gabor analysis, to understand this question a bit better. So then I need one more definition. Well, I will say very little, although one could talk much longer about this. So I say that G is in M1, so that the modulation space M1, and I think nowadays we always call it the Feichtinger algebra. If the following integral in the product of G with all time frequency shifts of G is absolutely integrable. Integral goes over R to D. So we may take that as a technical condition, but I need to make a few remarks. First of all, this is sort of bilinear, hard to deal with, but we could replace this one by phi arbitrary. So G is in modulation space M1 if the inner product of G with time frequency shifts of an arbitrary Schwartz function is integrable. This is, well, in a way it looks like a technical condition, but let's see, as soon as time frequency shifts, so these two operators are treated as, say, having the same meaning, so treated democratically, whenever you try to make conditions as general as possible, you will find this condition. So what one can show is Schwartz. So Schwartz functions are in M1. Well, if this is a Schwartz function, then this inner product will decay rapidly in Z, so it's integrable. And you can show that that this is M1 is a subspace of L1, and its Fourier transform is also subspace of L1. It's invariant under Fourier transform. If you apply Plancherel, then you have G hat here, and you have again time frequency shift here. So that's one set of inclusions. You might, for example, in dimension 1, if you don't want to deal with time frequency shifts, if the first three derivatives are in L1, then f is in M1. So there are plenty of embeddings that one can do. So in many contexts, that's a technical condition. In Vienna, we claim that's the canonical space that appears whenever you do time frequency analysis. If you want to know more, Hans Feichtinger is here, and he can give you a course over a semester just with this space. And he has a very innovative way to say build commutative harmonic analysis on M1. So there's a lot more to say. So now comes the second main statement. I call it the coarse structure of Gabor frames. So this is a theorem that works for all windows. It's sort of a general statement that you can say make about the frame set. So if G is in M1, well, I don't know, then the full frame set of G is an open subset in the manifold of all lattices. So lambda lattice, and it's now comes the main thing, the volume of the lattice strictly less than 1. And this subset also contains a neighborhood of, well, a fat 0. So this would correspond to all matrices with some norm less than epsilon. Okay, so there exists some epsilon, so that all lattices generated by matrices with norm less than epsilon generate a frame. So I say a neighborhood of the 0 lattice. So this would be the statement for the full frame set, and the statement for the reduced frame set is probably a little bit easier to digest. The reduced frame set is open in the set of all lattice parameters alpha beta in 0 infinity squared with alpha beta less than 1, and containing a neighborhood of the point 0, 0. Okay, so I will discuss the situation of rectangular lattices, because then one can make plots and show a little bit. So here is the first quadrant. Each point in the quadrant corresponds to a rectangular lattice. Okay? So now this statement says that if a lattice is in the frame set, so if a lattice alpha z cross beta z generates a frame, then the product alpha beta is below the hyperbola alpha beta equal 1. So here is the hyperbola alpha beta equal 1. So the lattices that can show up in the frame set are below this hyperbola. So below the hyperbola, there's a possibility to find a frame. Above the hyperbola and on the hyperbola cannot be a frame. And the third statement is there's a neighborhood of the origin. That's a little bit small. So, okay, let's do it this way. So there's a neighborhood of the origin where you surely find a frame. Okay? And the third statement, well, the fourth statement, this set is open. So if you have a point, so if you have a point in the frame set, then there's a whole neighborhood of points in the frame set. So it can perturb the parameter slightly, and the frame property is preserved. So I don't know what exactly I should say about this, because I do you a service. This summarizes essentially 50 papers with the main statements and main result, general results about Gabor frames. And I'm actually too lazy to mention all these papers, but essentially this summarizes these results into one definition and property of the frame set. So let me say a little bit more, nevertheless. So this condition here, or this condition here, is a necessary density condition. In order to generate a frame, I need the density to be sufficiently small, and there is a threshold, sort of a critical density, and you have to stay below this critical density. So density questions for sampling, it's a whole business, and this is one particular example of a density theorem. Let's see, what else? So if alpha beta is small, then we get the existence of Gabor frames. Okay, so if the lattice parameters are small enough, then we know for sure that the corresponding Gabor system is a frame. So this statement includes that for very general windows, Gabor frames always exist. The fact that the hyperbola alpha beta is excluded is known as the Balian-Low theorem. Actually goes back to physicists, and there's a whole industry in mathematics investigating all sorts of variations of Balian-Low theorem. I would say that okay, so alpha beta equal 1 is excluded. This is both the density theorem and the Balian-Low theorem can be interpreted as versions of the uncertainty principle. So and then the openness, Fg open, is a deformation result. If you change parameters, then points that say near 0 are close to each other as you go further out. So if you take alpha k beta L, and now you take alpha prime k beta prime L, these points may be far apart. So points that are naturally associated to each other may be far apart. So this is really a deformation. And this is a very important result. Actually, it's due to Hans Feichtinger and Norbert Keiblinger. We discovered last summer that it could be derived from a theorem in operator algebras by Jean Bélissard. And that paper actually contains lots of more information that is useful. But let me say one thing. Suppose you are on this critical hyperbola. If the deformation result is true, then you would have a whole neighborhood of lattices that would also be frame. And as you see, then you would have lattices that are in the forbidden zone. But the density theorem tells you that cannot be. So the density condition is an open condition. In certain fields where you do sampling, density is an open condition, say in complex analysis quite often, Fock space. And in some cases, the density conditions are not open. Fundamental example, Paley-Wiener space, band-limited functions. There you have frames actually basis at density 1. So this theorem for Gabor frames excludes anything meaningful in this sense at density 1.
Why do you say alpha beta 1 is a Valiant theorem? Why do you say alpha beta 1 is a Valiant theorem?
The Balian-Low theorem says that if you have a frame, equivalently a Riesz sequence at alpha beta equal 1, then the window cannot be in M1, or the window has infinite uncertainty. Okay, so each of these 4 items is a whole direction in Gabor analysis where, well, yeah, basically this here, necessary density, the Balian-Low, and the existence. You can already find them in the very first paper that investigated Gabor frames systematically, paper of Dobshi in '92. Well, not formulated in this way, but then each of these 4 items has created a whole industry. And when you try to reduce it to the essence, it's this statement. So there's one thing that I want to point out. The assumption that G is M1 is absolutely crucial for this to hold. And the counterexample would be the characteristic function 0, 1. It is not in the modulation space. Actually, maybe it's easy to see. So you have time frequency shifts of, so that's modulation, translation. Okay, so you have time frequency shifts of the characteristic function. Characteristic function is discontinuous. So if you take the product of G with a shift of G, still a characteristic function, still discontinuous, on a set of x of positive measure. So the Fourier transform of a discontinuous function cannot be in L1. That means this function is not so this function is not in the Fourier algebra, and so here you have a set of positive measure x, so that the corresponding inner products are not in L1 with respect to psi. So this is maybe one of the nicest windows. I think Q soon calls it the ideal window. It's not ideal for time frequency analysis. So first of all, if you take integer modulations, integer translates of the characteristic function, that's actually the very first example we looked at. This is an orthonormal basis. In particular, it is a frame. And alpha equal beta equal 1. So you have an orthonormal basis at the critical density. So for windows that are not in the Feichtinger algebra, the critical hyperbola may be part of the frame set. And I hope that tomorrow, if somebody can help me with copying, cutting out images from papers, then I will show you a little bit about the frame set. The frame set is very complicated. That's an insight of Guido Janssen, and he wrote about 40 pages about just special cases. And Q Soon, recently, last 2-3 years, gave a complete description of the frame set for the characteristic function. Reduced frame set, only rectangular lattices. The proof is about, well, the paper is 90 or 100 pages, and the theorem forces you to distinguish 18 cases and subcases. So this is a very special kind of mathematics with lots of case distinctions, and there is a characterization of this frame set. It's incredibly complicated. So if you are out for complicated stuff, omit the assumption M1 and see what happens. Well, in the last half year, the situation has changed a little bit, so I'm not sure that M1 is good enough to do anything. So let's see. So let me give you some hints how this theorem is connected to the duality theory. I mean, it's 50 papers and hundreds of pages devoted to 4 topics. And on the one hand, it's easy to state, sometimes not that hard to prove, but the sort of, this is a very abbreviated version. Okay, let's see. How do I do that? So maybe, so deformation implies, the deformation result implies the exclusion of the critical hyperbola. Clear, this is a stronger result than this. So for the density, I can give you a small argument. But it requires that you would know a little bit about frame theory or take it on faith. So basically, gamma equals S inverse of G. That's the canonical dual window of G. Depends on alpha, beta, whatnot. And then we write G. So that's S inverse G. So that's S gamma, so it's the frame operator applied to gamma, so there's some gamma pi lambda G, pi lambda G, lambda in the lattice. And on the other hand, this is 1 times G. Now, these coefficients are, say, the canonical coefficients to represent G. And there is a statement in frame theory that says that so in general, this is linearly dependent. You have many ways to represent a function as linear combinations of the frame vectors. And among all these, this is sort of a recipe that always works. These are the canonical frame coefficients. And there is a result in the very first paper of Duff and Scheffer on frames that says the canonical frame coefficients are those with minimum L2 norm. Okay, so if you think a little bit about how the reconstruction of F from the frame coefficients works, you see that there's a Moore-Penrose pseudo-inverse, and that indicates that what you obtain has something to do with least square problem. So Duff and Scheffer, I think in 1952, already showed these frame coefficients are the ones with smallest norm. So this means that gamma pi lambda g squared sum over lambda is less than or equal to 1. So all the other time frequency shifts have coefficient 0. So this is a representation with the smallest coefficients of smallest L2 norm. Okay, now, well, this is over the lattice, but at least this is certainly greater than or equal to the inner product of G with gamma squared. And what is this? The inner product of G with gamma, according to the biorthogonality, is exactly the volume of lambda, in this case squared. So done. Also, you might actually, maybe as exercises for this afternoon, suppose this is 1. Then you have equality everywhere. This means all inner products with lambda not equal 0 are 0. This means you actually, at critical density, you automatically have a basis, okay? And you can expand the duality theory a little bit if at critical density a frame is a basis. But essentially you can see it here. And this step requires just the main fact on frame representations. This linear algebra has nothing to do with Gabor frames. The existence, I guess I should stop soon.
Yeah, we started 5 minutes late.
That means I have 5 minutes. So maybe existence, yeah. So I want to give you a plausibility argument for the existence. Again, not a proof, just make it plausible. And for that, I take a slightly smaller class of windows. So we would assume that the, ambiguity function, the inner products of f with of G with time frequency shifts of G decays polynomially. To get integrability, we need that this goes like this. So let's see. Now I would choose R large enough such that, so what do I try to do? I want to show you that the Gramian on the adjoint lattice is diagonally dominant. So that means I have to, so the adjoint lattice is 1 over beta, 1 over alpha. So I have to take the terms of this, of the diagonal. So let's see, I would need that 1 plus k over beta L over alpha negative 2d minus epsilon c and sum over kl not equal 0. So this is less than or equal to, say, 1 minus delta times the 2 norm of G. So you believe me that if 1 over alpha, 1 over beta are greater than r, you can do that uniformly. So for alpha, beta less than 1 over r. Okay, so that's something you can do uniformly with delta positive. And then you look at the Gramian, pi nu g pi mu g. So you take the sum over nu not equal to 0. So that's the same as taking, not equal to mu. So I take the off-diagonal terms. So that's the same as sum g pi nu. Okay, now I write it down. K over beta L over alpha g sum k L not equal to 0. So I bring this over, and it's just this sum, and that would be less than 1 over delta times g squared. So here I have the so this means in each row, each column of the Gramian, the row sum is less than the value in the diagonal in a uniform way. So this means that the Gramian is diagonally dominant, and therefore the Gabor system on the adjoint lattice is a resequence, and therefore, okay, alpha beta is small enough, you get the frame for the rectangular lattice. So the analytic estimates have to be done here, and then you construct a Gramian that's diagonally dominant by using the decay. And the M1 is sort of as far as you can stretch this argument by replacing the polynomial decay by a uniform L1 decay. But that, again, would require more technicalities. I hope that this argument gives you a rough idea where the existence of Gabor frames for small lattice parameters comes from. So I think I should stop here. Thank you.
Thanks very much. Are there immediate questions?
Compactly supported? Yes. Then you had one? Oh, well, well, the answer is yes. We basically can multiply by anything of absolute value 1. So you can do a lot of things to modify this example. Yeah, well, there. See, outside M1, you run into trouble. So I cannot give clear answers because I've always sort of ignored that part of the Gabor universe.
You can take these ones?
No. Yeah. These plans. no. Actually, there's a complete characterization of frames at critical density. Let's take alpha beta equal 1. You can always dilate, so that's the case. And then is actually a Riesz basis if and only if the Zach transform, whatever that is bounded away from 0 and bounded. So, and this is a unitary operator from L2 to L2 of R to L2 of the square. And so any function of two variables that doesn't have zeros gives you a window that generates a basis at the critical density. Let's see. For that, you would need that this is a trigonometric polynomial in psi. So you construct a trigonometric polynomial in psi with certain additional periodicity properties in x, and you go back and you get something with compact support. I think Helmut Böttcher and Guido Janssen have thought a little bit about Gabor frames with compact supported windows.